Okay. Hello. Good morning. We are going to start this seminar, and the idea is to explain the works that the Building Energy and Environment Group is performing in relation to the assessment of the energy vulnerability and the climate vulnerability in general, and in districts or in big urban areas. And the way that we are going to model or to characterize this kind of energy vulnerability will be based on an intensive application of data-driven techniques, starting from harmonizing the data and followed by different artificial intelligence techniques that will be explained by Jose Manuel Broto. These works are included within a European funded project called Climate Ready Barcelona. Climate Ready Barcelona is a project funded by is at the European level, but it's not funded by the European Commission. It's funded by the Google Foundation, and it's managed by ICLEI. And we are 4 Catalan partners, and the pilot site or the area that is included in the project is the city of Barcelona. So I'm going to give the words to Jose Manuel Broto so that he can start explaining all the experiences and the works we are performing. So Jose Manuel, if you would like to start.
Hello everyone. My name is Jose Manuel. I will present this theme seminar, and I will say that this work is not only my work. We have a theme group, that are working on that. That is Antonio, Arnau, Maite, Jordi, and Gerard. Okay, what is energy vulnerability? The first one. Energy vulnerability is a subjective combination of risk factors in homes that can lead to energy poverty. There are 4 main risk factors, that is technological, social, economical, and physical. The first one, technological factor, is related to the inefficiency technology or old technology, all appliances, inadequate isolation, like the typology of heating, ventilation, air conditioning system, domestic appliance, and their usage. The second risk factor is a social factor. Social factor like socio-economic circumstance, income levels, household size, social support networks, health conditions. All these increase or determine the vulnerability to energy poverty. The third factor is economic factor, that is a financial constraint, not only house financial constraint like income, salary, or something like that, is also the energy cost that are relative to not by salary, that energy efficiency upgrades, and all this contributes to energy poverty for households. And the last one factor is physical factor. There are 2 factors. That is the extreme. The first one is related with the extreme weather events, like seasonal variation in energy demand, inadequate climate control measure, and so on. That all this can increase the energy demand, and especially in regions with prone to harsh climates. The second physical factor is the physical building attributes, such its age, construction quality, energy efficiency features, influence of energy consumption, and vulnerability to energy poverty. Okay, how we propose to assess the vulnerability of citizens through the implementation of we propose a methodology that integrates energy thermal building model to to obtain the energy demand and the temperature KPIs. All this will be explained later. Weather model to upscale mesoscale resolution to micro-local. The mesoscale resolution is about 8-kilometer grid resolution, and the micro-local is 100-meter resolution. All this I will explain later. The integration of interdisciplinary and highly heterogeneous data source. All these data sources need to be harmonized in a common way. We follow an ontology. The calculation and estimation of KPIs, the key performance indicator for each building is a key factor. And finally, the visualization of this KPI over a web interface and have the ability to users to play with them. As Jordi was saying, this is a ICLEI Action Fund 2 project that has a budget of 1 million euros. It's founded by ICLEI, that is a residential European association, and Google. The geographical scope is Barcelona City, and the objectives is the support to citizens and public authorities to anticipate and adapt to climate change effects and the energy crisis. To climate change effects is like heat waves. The period of implementation from this project is from July 2023 to June 2025. And the partners are the coordinator Eco Surveys, ABD, Bitgenoma, and us, CIMNE. So I start explaining the general architecture that we developed for this project. First of all, I start from the. I don't know if you see my mouse. When I start for the left side. First of all, we need to gather all the data from the data providers. This data can be open data portals like Barcelona Open Data or GenCat Open Data, INE, other data providers as satellite image like raster files or vegetation index, whatever. Other data provider is public APIs like datasets APIs to get the postal code consumption. Files from distributor like Neja or a distribution Endesa, and city council entities facilitate us data of consumption or social events. All these data are categorized in these types, that is vectorial files that are points, geometries, polygons, lines, files, raster file that is a cloud of points, tabular file that is tabular like time series. La meva energia in this project, one of the goals of this project is develop an app called La Meva Energia, where people that is in vulnerability situation now in Barcelona go to the energy advice points, and here they help these people with problem with consumption, or they can pay some invoice or whatever. They help these people. We develop an app. The pilot is starting in September. Also, the app is developed right now. In this app, all the vulnerability people introduce all the data that they have that we will see later. So all this data is an input for our model. We can attack third APIs and the same with third databases. So here we have our architecture. It's an architecture based on Kubernetes microservices. The first layer is the ingestor layer. In this layer, we have a client API like DataDis or other APIs that from these APIs we obtain all the data that we introduce in our graph database. And there are two other ingestor types, that is manual scripts. This is a script that we can run whenever we want, and chronify scripts. These scripts are run, for example, periodically. For example, cadaster data are updated every 6 months. So we have jobs like every 6 months download this data. Or Meteo Galicia forecast data, they are updated every day at 6 a.m. At 7 a.m. we have a cron job that we get this data and introduce in our storage. All this data that we gather is introduced in another second layer, that is the harmonizer layer. This layer is helped by the ontology that we will be later. All this data follow the ontology, and with the RML files, we harmonize this data to the ontology and introduce in our database. Our database is split in two databases. One is a graph database that is we have here the ontology relation and all the structure of the data, and a time series database. We have here all the data, the consumption data, weather data, all the time series data. Both databases are connected. Once we have the data in the database, we have a thermal model, demand model, that we run to obtain the indoor KPI temperature and demand energy. We have a weather upscaling resolution model, and with all this data that we have in the database, we make a transformation and obtain these KPIs. But we have not all the KPIs. We have what space. We have data that is secret data or privacy data. So with all this data, we have a graph neural network that complete all the data, and the data is returned to the graph database, graph and time series database, and this data finally with a API go to the user interface and the third-party apps. I will explain you a little bit all the heterogeneous dataset that we have. The first one and the most important, because we are analyzing the climate vulnerability at building level, so we need the building level. We have the from cadaster, spine cadaster, that are harmonized to Spire. We have the geometry, built areas like gross floor area, built up plant area, the number of floors below and below ground, the number of dwelling, the building units of the building, the usage, the state, if the building is functional, ruin and decline or whatever. The level, the geolocation level is a building level, and we obtain this file as the R vectorial file. The second one is the energy performance certificates. We obtain it from the Catalonian Open Data. The geolocation level is a dwelling level, and here we have the qualification, date, location by address and coordinates from all the EPCs. We start with the consumption files. we have a consumption file that are yearly gas consumption and electricity consumption for at building level for the whole Barcelona city. Only for 1 year from the 2017 year. This is an Excel file. We collaborate with the AMB, and this file will be facilitated by them. The second file that is electricity consumption, that is from a distribution in Endesa. And here we have a monthly electricity consumption, number of cubes, street number, street name at building level. We have also gas consumption, yearly gas consumption from Netgia at building level. We also have electricity consumption from datasets, that is a public API that we can get hourly electricity consumption from at postal code level, but with the distinction of economic sector and tariffs. It will be useful because we can play with, if we want to know the climate vulnerability index, we usually want to know in residential house. And here we can obtain this data. Other data set that is not a data set, is like a model, is a building thermal demand. The attributes that we get is the indoor temperature and the energy demand. We have the geolocation level is a building level, and this is, well, the calculation is based on an energy plus simulation with a set of archetypes and so on. Here we have the surveys that we obtain from the Lameva Energy app. And in these surveys, with these surveys we can locate where is the building where these people live, the date of the survey, the gender of the people, the consumptions, economics factor, social factor, and so on. There is like 60 questions, so we can obtain a good information from here. And the surveys initially are at dwelling level, but we aggregate to building level because we want problems with the low PD. From weather data, we have two weather data sets. The first one is ERAS 5 LAN, and from here we get the date, the temperature, humidity, wind speed, apparent temperature, and the location from these measures. The location level is a 10 kilometers grid for each postal code, and the format is a CSV file. From the socioeconomic data, we get the data from the INE, that is the National Institute of Statistics National Institute. And here we get the incomes, the income source, the demography, the population, and so on, and very much data. But we also have the climate shelter, and we are in the climate. We're trying to know the climate vulnerability of the city. We need to put the climate shelters. Climate shelters are distributed by the whole city, and we have the location, the name, the schedule, because we have a climate shelter and it's closed. This is not relevant, and the creation data and modification of this climate shelter. We get from this data from Barcelona Open Data, and it's a building level. Now we start with the administrative layers. The first one is the postal code. We use the postal code layer to geolocate or to know where are the buildings or the relation between them, and we get the postal code name and code from here. The same for the census tract. We use for the same for the postal code, but with the census tract. The same for districts. As the project is it's only in Barcelona city, we have the districts in the city. The same for municipalities, neighborhood. We have the geometries, names of municipalities and neighborhoods and codes. Now we enter in the raster file. The raster files vegetation index is it's a normalized different vegetation index, and it's a raster file that is a cloud of points where every pixel is a one square meter of the Catalonia measure, and this measure is from the cartographic. We also have the tourist establishments. From the tourist establishment, we have a building level, and we have the location, the category, hotels or the category from this hotel or whatever, and the capacity and the state, if they are closed or not, or which times. Or we have camping, hotels, rural tourist apartments, and home for tourist use. This is a good point. With this, we can know where in the city there are a lot of dwellings that the user is not primary dwellings, that is like tourist dwellings. It is important to know to assess the vulnerability index. Two very important datasets are the technical inspection of buildings. We obtain this data from the GenCat, and the attributes are the description of the building, the equipments, their defects, are the inefficiencies. We obtain this for a building level. And other kind of the technical inspection of buildings are the one years ago in the Barcelona City Council do that extremely detailed technical inspection from the Besos district from 2,000 dwellings, and this we are trying to obtain this data. We don't have this data right now. We also have data of mortality and morbidity. That is very important due to heat waves, and the aggregation level is a primary care center, and we obtain this from the Barcelona Health Agency. And finally, the weather forecasting that we obtain for Meteo Galicia, and we have the temperature, humidity, and location at aggregation level of 8 kilometer grid. So with all this data, you can see that is very heterogeneous. For do a data-driven model, we can form a knowledge graph, the knowledge graph of the project. And now all this data we need to ingest in our database. The first is gather the data manually or periodically. Is the same that I explained before. Reading from webs with web scraping or attack apps, APIs or other database, and all this is developed in Python. The second step is the harmonization process. All these datasets grow. If we need to follow an ontology, because if all the data are in the same format, later we can play with them. And this step is a key factor, the RML library. It's a key library. Here we have the group ontology. In the group ontology, I don't want to explain you what is all this box, but white box in ontology is an important point is the reusability. So in this structure, you can see that white box are a reusability box from other ontologies. Here we have the ontologies that we have, and blue box are classes that we need to implement because our projects demand these classes. As you can see, more or less the 90 or 95% is reused. It's a good point. The most reused ontologies in our ontology is the Saref group for buildings and device, the SSN from systems and deployments, and the geospatial for geolocate features like buildings or whatever, and the QDT for units, for unit of measurement or kilowatt hour or square meter or whatever. Thanks to this reusability, we realize that we need the reuse ontology to take profit of the advantages that offer ontologies. The way we'll explain later. Thanks to the well-defined ontology, we use it in many projects without many change of this ontology. These are all the projects that we use ontology right now. So once we have the data harmonized, we need to harmonize it. We need to store it in a graph database. A graph database is not mandatory, but if we are using ontology, we want to save these relations between classes in some place. So ontologies represent structuring knowledge, emphasizing a relationship between entities. And graph database excel in modeling and querying complex relationships, making them a natural fit for ontological data. Graph database allow us for adaptable data models. Graph database naturally model complex relationship, facilitating querying and transversal. They have a good and efficiency scalability. They have a powerful querying that are robust and have many querying capabilities, including traversing relationships effectively. And one of the most important is the semantic reasoning, that a graph database support semantic reasoning like inference. Inference is like when the ontology is well defined, you harmonize the data, and if you don't remember some relation or you don't want to define some relation, the graph database can define by you, and this is the inference. That is very important. So we use Neo4j for graph database. That is, is offer all that I say before. And we use also SACL. SACL is a validator. In the SACL we define a constraints, and all the data before that we introduce in the graph database are validated with this validation. We ensure that we have the integrity, consistency, and compliance with the predefined rules. So we have two databases, the graph database and now the time series database. If we store all the time series database and the structure of the ontology in a graph database, the database throw a very weak weightlessly, and the queries take a long time to finalize, and we realize that we need a time series database that finally tuned for storing and querying time data. If we use the indexing strategies for time-based queries, we can optimize the storage and the data retrieval. We have a good scalability because we only insert here the time series data, so it can handle a massive time series data volumes efficiency and offer built-in functionalities like downsampling, aggregation, and windowing operations from the time series data. Before we use a NoSQL database that is called HBase, and now we use a Druid Apache Druid database. That is this database is perfect. Have a good time queries response, and also has a good time series database for store tabular data. This database, the graph and the time series database are merged, like it works on like one database. The first one are focused on the structural data, managing the ontological relationships, and the second one harness each database technology strength for the time series. We start with the modeling. In this project, we define three main models. The first one is the building thermal energy model. That is a simulation of energy demand of buildings in urban area based on archetypes, construction types, local weather, and user behavior patterns. The second model is a weather upscaling resolution model that we predict a grid of 100-meter grid with original data from 8-kilometer grid. And the last one is a graph neural networks that is a general model to predict indicators at building level based on real measurements, location of buildings, and the relation between buildings and aggregation layers like postal codes and subtracts. The first model is the thermal demand energy model. As input, we have the building archetypes from the Barcelona city that are based on the age, on the building characteristics, and so on. The orientation and distance to other buildings. As we have the fingerprint of the building, we can and the geometries, we can know where is the location of the building, where it have other buildings, if the street in that where this building is a 5-meter street or a 50-meter street. All this we put here as input. The envelope transmittance, the envelope air thickness, the user behavior patterns, the user temperature set points, the heating, ventilation, air conditioner systems, and the micro local weather that we have. With all this, we generate a combinational matrix of all these buildings, all these variations. We split this data into datasets, And the 30% of the case comes from an energy plus simulation that run only deterministic simulation of 1 year. This simulation, as output, we obtain a monthly aggregation energy demand and indoor temperature KPIs. With this output that is are only for the 30% of the case, we train and validate a neural network model using the building parameters as input, that are this one that we combine, and a KPI as outputs, that are these KPIs, temperature KPIs, and energy demand. Once we have this model train and validate, with the other 70% of case, we get or we estimate the monthly aggregation energy demand and indoor temperature, but these are estimate, and these are simulate. These are quite different. We do the in this form because energy plus simulation time is very large in other case. So we simulate only 30% of the case, and we train a neural network model for simulate the 70%. We improve a lot of the time. Once we have the two energy demand and temperature, indoor temperature, we assign the most suitable result to each building in the Barcelona city. So here we have a thermal model for all the city, and if we change data from this input data, like people that want to change his windows or his whatever to improve the energy demand, we can make with this model training, we can make future simulations. The second model is the weather upscaling model. As input data, we have the Meteo Galicia datasets. That is a 96-hour horizon historical forecast from 2008 to 2017. We also have this data. We obtain the temperature and the relative humidity. Between point and point, there are around 8 kilometers. So it's not, at this resolution, is not useful for the Barcelona city. And as static data, we have the cadaster. From here, we obtain the total bit volume. These indicators are aggregated over 10% meter grid. We also have the vegetation index. With this data, we obtain the percentage area, and with the I don't put here, but with this data, we obtain the vegetation index in a 100-meter grid. The digital terrain model for obtaining the average height over the sea level. The land cover map, where we obtain the percentage area dedicated to every land cover typology. With all this data, we create a model, we train and validate a model, and we use as output the climate variables for cities in Europe from 2008 and 2017 based on UrbanClim model. This dataset are in a 100 resolution, in a 100-meter resolution. So with all this data, with this input data and this output, we try to train and validate a model. The model that we obtain, we have the air temperature and relative humidity from a 96 horizon forecast. With this weather scaling model, we try to define when or to predict when when we will a heat wave will comes, and if the buildings that where the heat wave is more critical, as we have all the building characteristics, we can in our models we can say where are the high condition or where are the buildings more vulnerable, and we post a message in the app. The last model is the simplified knowledge graph model, and this model get all the data from the databases, make some transformation and calculate some KPIs that are here. We have KPIs from building characteristics, from socio-economic, from energy, from vulnerability, and from health and environment. These KPIs are validated for all the project partners, but when we calculate these KPIs, we have white spaces, so we need a model that fill all these white spaces. This model is a graph neural network, and with the real data and the estimated data, we have a knowledge graph complete. More or less, the knowledge graph or the neural network that we use is a heterogeneous temporal graph neural networks. As you can see here, all these, the square, the triangle, the circle, the oval, all these are, for example, the circle is a building, the oval a district, and here we have the relation between them. Now we are only watch the first image, but we have the relation with other buildings, like the circle is a building. We have the relation with a postal code because a building is a postal code, and so on. Once we have all this relation, we have the time variable. So we have this relation during the time. Maybe this relation can change. Okay, and this influence the model. So once we have all this data, we have an API to communicate the data. The API is a Flash Python API that has a Swagger to a better documented the API. All this Python is Dockerized in a Docker, and the Docker is running in a Kubernetes pod. From this API, we can get all the indicators. Indicators are KPIs. We can get single indicators. We can post a model of the request that comes from the app. We can get the model of the request from the app, or we can get model request predictions. And we also have the login with a beer token. We also develop a Python library called strip maps that it was developed to easily update a database from the Spanish territory. The main, also the base geometry of this database are the national cadaster addresses, and from this database, this data is enriched with the metadata of postal codes, census tract, neighborhoods, district, parcelized land, that is like 10 or 20 buildings, the main usage of the building, the number of dwellings, and well, the height of the building, so on. And this library is used in this project in two parts. In the app part to geolocate the buildings where the surveys are, where the people that fill the surveys are or are living. And in the other part, we use in the vulnerability map to harmonize, to geolocate all the data that we are harmonizing. The surveys or the data sharing with the Meva Energia. As I say, this is from here in the in the right side is our architecture, and here is the data app backend. In the backend there is a Mongo database that have stored all the surveys that people fill, vulnerability people fill, and here we have the address, the floor, the door, the dwellings, the ID of these people, and so on, and the answer of all the questions that are social, economical, and so on. So we can get three requests: one at building level, a cadaster island level, and a census tract level. The more accuracy is a building level that we delete because low PD. We delete the floor, the door, and the person identifier, and some questions. And this data is only we can obtain this data only if the number of dwellings is higher than 5. Because if we have a building that has only one family live here, and we can know that directly that this family fill the survey. And the other model that is the cadaster island, that is there are the same fields were deleted, but there are no filters because we have a higher aggregation, and the same from the census tract that we have a higher aggregation. Once with the weather model, once we get the alerts of the high conditions in several buildings, we post through the app backend these alerts here with the same API. The method post climate alerts. So as a user interface, first once we are seeing a lot of vulnerability, energy vulnerability, social vulnerability. So vulnerability is a function of exposure, sensitivity, and adaptive capacity. In our case, is climate vulnerability, so it's a function of exposure, sensitivity, and adaptive capacity to climate events like heat waves in Barcelona case. We see a lot of vulnerability, climate vulnerability index, and each author relates them at has his own criteria. In this project, a vulnerability map at the building level has to be implemented, and several climate vulnerability index will be defined. But as there is not a true or a right vulnerability index, the user will be allowed to see the different KPIs on the map from the whole Barcelona city and build his own vulnerability index. And that's all. If there is any question.
Thank you very much, Jose. It was a very nice presentation. Impressive work. I have a few minutes to ask some questions if anybody wants to. I was wondering, when you talk about the, yeah,
Sorry.
uh,
I am Aurora Monge. I can ask some question or?
yeah, go ahead.
Yes. Thank you. I am Aurora. I know Gerard and some of your colleagues from the Urban Mome seminar. And as you know, we have other projects similar to this called Climate Ready. And very interesting, very powerful, your project. I am super impressed. And I want to know, how do you detect the building archetypes?
Yeah, the building archetypes. There are previous studies from the Barcelona city for other companies, and we see where. I can say you right now. I don't know, but there is.
Yeah, it's Jose Manuel. I can add something to that, if you would like.
Yeah.
Yeah, the archetypes were defined by the research center, which is owned by the metropolitan area of Barcelona. I think it's I don't exactly remember the name, but they work together with the urban planning department, and they made a detailed study or analysis of the most frequent building typologies that are in the city of Barcelona, also in the metropolitan area. So they define it, I don't exactly remember the overall number, but they define some representative archetypes that are most frequent at census level. So for each census code, they identify the most significant archetypes. And then this institute and the AMB, they translated these archetypes into some geometrical defined 3D models made in using Energy Plus. And this is the basis we are going to use.
But specifically in one street, no? Because you are going to map it. You are in one street and you have one rectangle, no? And no. How do you say this is archetype 1 or 2 or 3? Because we have some problems with that.
Yeah. No. What they did was they defined the archetypes, and they clustered the existing building stock in these different archetypes. So they distributed these archetypes along the city. But in our case, we are not going to use the archetypes directly, the information of the archetypes directly. We are going to simulate a large amount of scenarios of retrofitting or of changing situations. For instance, archetype 1, we are going to simulate it in facing south, facing west, facing different orientations, and we are going to generate a large amount of potential possibilities. And then these potential possibilities will be identified within our knowledge graph. But we are not going to make it exactly as they are as they should be physically placed in the city.
Okay.
So
okay.
It's not exactly the same approach that you normally follow when you try to simulate the energy performance of an existing system, city, using white box models such as Energy Plus. You normally classify the building stock into these representative archetypes, and then you simulate them and you spread all over the city with a georeferenciation. In our case, we are not going to make it in the same way. Our idea is to generate a random number of possibilities in order to train a neural network. So it is slightly different. So the archetypes were defined based on the reality, but the results of the simulations are not going to be applied directly in the building that is placed in the city.
Okay. Thank you very much, Jordi.
Thank you, Jordi. Thank you, Jose. Thank you, Aurora. Is there any other short question? Okay. If there are no more questions, then I think we can close the session here. Thank you again, Jose and Jordi, for your contribution, and thank you everybody for assisting to this session of the Similar Seminar course, and see you all in the next session.
Thank you very much.
Bye-bye.
Thank you. Bye.
Bye.